It's math time with Heinz. It's math time with Heinz. Math time.
Hi everybody, so in lesson 6 here, we're going to be talking about factoring for the first time, which leads us into the second half of Unit 1. So lesson 6, we're going to review 2 factoring techniques from Algebra 1, where we talked about the greatest common factor, the GCF, and the difference of perfect squares. So to get us started here, let's prove this polynomial identity. So an identity is a statement that is always true. It's a statement that's always true. It's a fact. It's an identity. The left-hand side is exactly the same as the right-hand side. So I want to prove here that a squared minus b squared, something squared minus something else squared, always equals a plus b times a minus b. So I'm going to start with this side and make it look like that. So I'm going to find the product of a plus b times a minus b. And if I want to find a product, I'm going to make a table to quickly apply the distributive property, a plus b, a minus b. I get a squared, ab, a times negative b is negative ab. Sparky's acting up again. There we go, negative ab. B times negative b is negative b squared. So when I find that product and apply the distributive property, I get a squared plus ab minus b squared. And then the next thing, I'm going to say, what does that equal? Well, that equals these two middle terms here look like they're adding to 0, don't they? ab minus ab, those are opposites, so those terms add to 0. These terms here add to 0, so we get a squared minus b squared. I took one side of the equation and made it look like the other one. I took the right-hand side of the equation and made it look like the left. So this statement is always true, and this is going to pop up later on. This has to deal with that difference of perfect squares idea. But before we get there, let's talk about a little GCF factoring. Let's talk about a greatest common factor. So GCF factoring, all we're doing is we're undoing the distributive property. We are undistributing, we're doing the distributive property in reverse. We are so used to drawing the little arrows and moving that value in. Well, in this case here, we're not doing that. We're gonna undistribute some factor from every term. So if I had this trinomial here, 6x squared, 18x, and 10, we need to ask ourselves, what can I divide all of those terms by? What was distributed in? What can I undistribute from this polynomial? So I look at the numbers, 6, 18, and 10. What can I divide 6, 18, and 10 by? Not 3. I'm thinking it's just 2. So I'm going to undistribute a factor of 2 from that expression. And I'm left with, well, what am I left with? What times 2 is 6x squared? Well, 3x squared. What times 2 is 18x? 9x. What times 2 is 10? Positive 5. Well, notice that I can't factor out an x from everybody. Notice that I can't factor out x from each of these terms because not everybody has a factor of x. That plain old constant 10 there doesn't have a factor of x in it, so I can only factor out a 2. In this next expression, what can I GCF out? What can I undistribute from all of these terms here is the question. Well, let's look at 3 and 18. I can definitely take out a factor of 3. What about x to the third, right? That's 3 times x times x times x. Well, I can take out a factor of x. I can undistribute one of those factors of x. And I'm left with what? What times 3x is 3x to the third? Well, x squared. And what times 3x is 18x? 6. And that's all we had to do there. All I'm doing is I'm factoring out the greatest common factor. I'm factoring out that common term that each term of the polynomial, that common factor that each term of the polynomial has. So the first thing I like to do is look at the numbers. 2, 6, 18, and 54. Well, I can definitely take out a 2 from each of those terms. And then I look at the variables and I take out the lowest powered variable that I can. I take out which exponent, which term has the least power, if everyone has at least one variable. So to the fourth, to the third, to the squared, everybody has at least one factor of d that I can take out. There's one factor of d that I can undistribute from each of those terms. So I'm left with, what times 2d is 2d to the fourth? Well, d cubed. What times 2d is 6d to the third? Well, that'd be 3d squared. What times 2d is negative 8? I took out a 2, and I took out a factor of d. And then I'm dividing by 2, and that's it. That's all we have to do there, is divide everybody by 2, and we took away a factor of d from each term. We're just taking out the greatest common factor right now. And finally, look at the numbers, 5, 30, and 3. There's no greatest, well, there is a greatest common factor, it's the number 1, but we don't really write out a GCF if we're just factoring out a 1. So let's look at our variables, x to the third, x squared, and x. Everybody's got an x they can lose. Y squared, y, everybody's got a y they can lose. So I'm factoring out here a factor of x as well as a factor of y from each of these terms. So this first term, the 5 is still there. I factored out an x, and I factored out the y already. Because if I could always check by redistributing that monomial outside back in. All right, I didn't touch the numbers. I took out an x, and I took out a factor of y. So those guys got knocked down a power. And then finally, I took out a factor of x, and I took out a factor of y, and there you have it. So the greatest common factor isn't that bad to do, folks. You've been doing it for a while. You just need to look at the numbers, see what you can divide, and then look at the variables and see what factor everybody has in common. Well, here's the thing. In Algebra 2, you might not just be taking out a monomial. Your greatest common factor just doesn't have to be a 2. So we're going to practice seeing the structure here, seeing the structure of these polynomials and how we can use that structure. How can we use that structure to reveal the true shape, the true form of these polynomials? So let's look at this first one. I've got 2x times x plus 5, that's one term, minus 3 times x plus 5, which is another term. We have to think of them as a chunk. You can't view it as two separate things. That x plus 5 is one chunk here. So this kind of has the form of 2x times y minus 3y. That x plus 5 I need to think of as one item, as one chunk there that I'm going to end up undistributing. So if I replace it with a y, if I factor out that y there, what am I left with? Well, 2x minus 3. So this is kind of in la-la land over there where it's not really the problem. I need to look at this and say, both of these terms have a factor of x plus 5. That's what that y is representing there. That y is representing that factor of x plus 5 that I'm factoring out there. So that's my y. I undistributed that x plus 5 from both terms, and what's left? What's left over is a 2x minus 3. So it looks really different because we're treating that x plus 5 as one item. So we need to just wrap our brains around the fact that we can sometimes factor out a binomial or even a trinomial like we're going to see. So this next one, we're looking for a common factor. We're looking for what do these polynomials have in common. So again, I have two terms here. I have x squared times 3x plus 5, and then I have 16 times 3x plus 5. And hopefully you noticed both of these terms here, both terms have a factor of 3x plus 5. That's what I'm going to factor out. I'm undistributing that 3x plus 5. And what am I left with? I'm left with x squared plus 16. I'm left with x squared plus 16. I undistributed that 3x plus 5. That chunk got undistributed out. Down here again, I have two terms. I have two terms, and I need to figure out what do those terms have in common. And hopefully you realize here that they both have this t squared plus 5t plus 6. They both have this trinomial factor in common. So that's what we're actually going to undistribute out. I'm going to undistribute that trinomial there. I'm GCF factoring out that trinomial, and I have to see what I'm left with. Well, what am I left with? I'm left with t minus 2. That was what I distributed that trinomial into. If I treat this as one chunk, all I'm doing is distributing it like that. That's how you can check your work. And finally, this last one here. This last one here, I need to look for a common factor. Well, let's see how many terms I have. Now, right now, I kind of have 3 separate terms. And wait a minute, it looks like all of these terms have this factor of k plus 4. It looks like every term there has that factor of k plus 4 that I'm going to undistribute from all 3. I'm going to undistribute that factor from all 3 terms there. I got to grab my computer charger. I will be right back. I don't think I can pause my recording. I don't need my computer to die while I'm making this video. That would be terrible. And I would be sad. Here we go, plugging on in. So while I plug this in here, why don't you finish factoring that polynomial so that way it's done when I get back to the board. So hopefully, in that awkward pause there, that we're all going to talk about in class when you see me again, we're going to factor out that k plus 4, and then now the question is, what's left over? What's left over? What was left behind? Well, I have a k squared, I have an 8k, and I have a 12. That's how I can GCF out that k plus 4. So we've done some 9th grade GCF. Well, yeah, you factored out the 2. But in Algebra 2, we can expand our ideas of GCF factoring to factoring out chunks of binomials or trinomials. All right, let's do a little rapid fire factoring of difference of squares. So the difference of squares, I like to call it the difference of perfect squares or DOPS, is that form of something squared minus something else squared. Or if we go to smiley face land, it's smiley face squared minus chicken nuggets squared. So if I have 2 things squared connected by a minus sign, I can use that idea that it's the first guy minus the second guy, the first guy plus the second guy. So smiley face minus chicken nugget times smiley face plus chicken nugget. That's how I can rewrite that structure of the difference of perfect squares. And the key thing is it's the difference. It's not the sum, it's the difference of perfect squares. So hopefully when you see x squared minus 25, your Algebra 1 teacher taught you to say, wait a minute, I can factor that, I can rewrite it as a multiplication problem as, well, what made x squared? X times x. What makes 25? Well, a negative 5 and a positive 5, so that way that middle term drops out. That wasn't too bad. Let's see how this one goes. Is it the difference of perfect squares? Well, it's the difference because there is a minus sign. 1 is a perfect square. 1 times 1 is 1. And those look like perfect squares to me, so 1 times 1. What gives me 9y squared is 3y and plus 3y. That's it. That's how we factor the difference of squares. It takes you recognizing the structure and running with it from there. Let's see how bad this one can be. I got to the, okay, I can do this. I'm going to say, all right, it's the difference, and these look like perfect squares to me because 9y squared and 9y squared makes 81y to the 4th. And then I'm going to do a plus and a minus 16x to the, all right, this is also perfect squares. I've got 4x squared and 4x squared. Nice. But wait, there's more, said Billy Mays. Rest in peace, Billy Mays. But look what we've got sitting in front of us again. So you know those little Russian dolls where you open them up and then there's another one inside? That happens a lot of the times when we're dealing with the difference of perfect squares. So right here, we've got DOPS again. We've got the difference of perfect squares popping up again because I have 9 and 4, which are perfect squares, as well as y squared and x squared. And they're connected by a minus sign. So I've got 3y and 3y. I've got to fix this smartboard because I'm going to lose my mind if it keeps doing that. Minus 2x plus 2x, because that's what made 4x squared. So we can break down the difference of perfect squares even more. What I do want you to notice is that you cannot factor this expression anymore because of that stinking plus sign there. That term with the plus sign just comes along for the ride until we get to unit 2. It's not factorable right now. You can't factor the sum of perfect squares. SOPs is no good. Right now we can't factor the sum of perfect squares. We'll wait till the next unit. For the sake of time, I've been talking way too long. We're not going to do that division. We're just going to get to these guys right here, and then we're almost done with this lesson. So factor the expression completely. How am I doing on time here? Perfect. Factor this expression completely. When I factor things completely, I have to do a couple steps of factoring. So right now, the only two things we've got are GCF, and then we're going to look for difference of squares. So right now we've got GCF, and then we're going to look for the difference of perfect squares. So let's look at this first term here, this first expression. Y minus y to the fifth. Well, I can factor out a y from both of those terms. Both of those terms have a factor of y that I can take out. Well, what am I left with? Well, what times y is y? 1 minus, well, I took away a y, so y to the fourth. But that right there, wait a minute, is the difference, there's a minus sign, of perfect squares. 1 times 1 minus y squared and plus y squared. But wait, look what sneaky Heinz. That's really sneaky Heinz, because look what we've got right there again. Like I said, difference of perfect squares likes to live inside of itself. I've got another 1 minus y, 1 plus y, because those are both perfect squares again. Everybody else comes along for the ride. That GCF of y, you can't lose him. Don't lose your GCF. And then we can't factor this thing as much as we want to because it has that sum, it has that plus sign there. We can't factor that 1 plus y squared. Not too bad. We can do that, right? I hope you can. All right, 2x to the, definitely not squares, because GCF. Let's factor out a GCF here. So what can I factor out from 2x to the third minus 18x? Well, I can take out a factor of 2 and an x, and I'm left with what? I'm left with x squared, okay, divide by x squared minus 9, which, now that's the difference of perfect squares. That's the classic example from 9th grade, folks. How do I factor x squared minus 9? Well, I factor it as x minus 3x plus 3, and my GCF is going to come along for the ride. Oh, this is going to be a doozy here. I can already tell you that. I can already tell you that because it's got that x to the 8th. So let's get to it. It's a difference, and I think these are perfect squares because what makes x to the 8th? Well, x to the 4th times x to the 4th plus 1 minus 1. Oh no. Because that right there is another set of difference of squares. Well, what makes x to the 4th? Well, that would be x squared and x squared plus 1 minus 1. Don't forget, this comes along for the ride. We have to bring on down that term we didn't factor. And I'm not factoring that because it's a sum. It's got the plus sign there. Not factoring this because he's got a sum. He's got a sum, but this, ooh, that looks like the difference of perfect squares again. I'm going to change the order I did that in so it looks the same. So I did difference of perfect squares once, did it again, did it for a third time, and then we bring everybody down because no factors get left behind. Be a great law that Congress should pass. No factors left behind. Hopefully this is all coming back to you and you're not scared that I'm saying the F word factor. Hopefully you're not too nervous that I'm saying the F word factor here. All right, let's do, I don't know, we'll do 2 of these. Sure, we'll do 2 of these and we'll actually, let's just jump to number 7 and we'll call it a day because this video is getting a little lengthy. So let's factor, if only Mrs. Dolan didn't call in the middle of it. Factor the expression here completely. Oh, all right, so let's see what we've got. Let's see what we've got here. Well, I'm seeing a 2-termed expression. That thing and that thing, which thankfully, I wanted a highlighter, which thankfully they both have that common factor. So let's undistribute that common factor of x to the 4th minus 16. Which leaves me with x to the 6th, y to the 4th, minus 9. All right, I can do this. I can do this, because now I'm looking for the difference of perfect, this is the difference of perfect squares. I can factor that as, well, what makes x to the 4th and what makes 16? Well, it's x squared and x squared. Minus 4 plus, are you kidding me, Heinz? Come on, coach. We've got another difference of perfect squares there. We've got x minus 2, x plus 2. But wait, I'm not touching this one. Can't touch this. Dun, 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 dun. I can't touch that because it's got the sum. It's got a plus sign there. All right, now let's tackle this bad boy over here. It's got a minus sign. X to the 6th, I think, is x to the 3rd, y squared. Yep, that does it. Minus 3 plus 3. And then I'm going to give that one more look because I'm just going to bring those guys down because those aren't squares. 3 is not a perfect square. What nice integer times itself gives me 3? Nothing. It's some crazy irrational number. So that's how we factor that completely. So notice we learned we reviewed 2 factoring techniques in this lesson. We reviewed how to factor the difference of perfect squares, which is that smiley face plus chicken nugget, smiley face minus chicken nugget technique, as well as went over how to take out a GCF, how to take out that greatest common factor. And I'll see you in person or in another video. No one ever knows. Bye, guys.